popularly known as Oracle. Today we'll be looking at lenses. Lens, what's the lens we have on board? A lens is an optically transparent medium bounded by two spherical refracting surfaces. Take note of this word, bounded by two spherical refracting surfaces, or a plane and a spherical surface. Now, what's about that? You see, this is a lens having two spherical surfaces. This is also a lens having two spherical surfaces. This is a lens having a plane and a spherical surface, a plane and another spherical surfaces. These are spherical surfaces but in the form of meniscus. So what do we have them as? Now you see we have two types of lens generally. One is called the convex lens and the second is called a concave lens. Now under a convex lens, we have the biconvex. What are biconvex lenses? Biconvex lenses they are lenses that you have two spherical surfaces. So it's either a biconvex lens or a biconcave lens. So bilenses are lenses with two spherical surfaces. So for the concave, this is how you have, for the convex, this is how it is written. For the concave, this is how it is written. This is a biconvex lens. This is a biconcave lens. Now, what about for the one with a plane surface and with a spherical surface? A plane surface and a spherical surface. Those lenses are called a plano lens. So these are called plano lenses. These are called plano lenses. Plano. These are called plano lenses. Why these are called bilenses? Then why these are called meniscus lenses? So if you see them here, this is a biconvex lens. This is a biconcave lens. This is a plano convex lens. This is a plano concave lens. Why this a meniscus concave? A meniscus convex lens. Why this a meniscus convex concave lens? Now take note, what's another name for a meniscus convex lens? Is also called concavo convex. Another name for meniscus convex lens is also called concavo convex, while another name for meniscus concave lens is also called convexo concave. Take note of this. This is very important. It's an exam question. This is very important. It's an exam question. Now, I'll show you a convex lens. This is a convex lens, while this is a concave lens. Now remember from our mirror class, a concave mirror actually converges rays of light. But for a lens, a convex lens converges rays of light. A mirror, a convex mirror diverges rays of light, but in lens, a concave lens is what is not diverging. So what the mirror does is what is the opposite that the lens is doing. So this is a convex lens. It helps to converge rays of light to a point, while this is a concave lens. It helps to diverge rays of light. Now, if this is being diverged, this place becomes the focus. This is our focus. Rather, this is our focus. So the next thing we'll be doing now is I'll be showing you ray diagram. Now let's look at image formation in convex lenses. Now, convex lenses can produce various kinds of image or images depending on where the object is being placed. Like for example, number one, we have the object in between the principal focus and the optical center of the lens. Now take note, the center of the lens is called the optical center, and that's the point in the lens where light passes through undeviated. We have such in a mirror also. There is a point in the mirror where light passes undeviated. That part is called the center of curvature. Light goes through the center of curvature undeviated. Now, If an object is placed in between F and the optical center of the mirror, what happens? We have the image formed behind the object. We have the image formed behind the object. Now, please look at this. The image is erect. The image is erect, is virtual and magnified. Virtual, erect, and magnified. That's the kind of image you have here. When an object is placed between F and the optical center, you have a virtual image, you have an erect image, and a magnified image. What about when the object is now pushed to the principal focus, which is F? We have the image is at infinity. Now, this image at infinity is real, is inverted, and it's magnified. The image is real, is inverted, and is magnified. Wherever the rays will meet, that's where the image will be formed. It is re-inverted and magnified. Look at number three. Number three, the object is now between 2F and F. Now, what about this? It's looking like the same way we did between C and F, between C and F as regards a concave mirror. Now, between 2F and F, we have the image beyond 2F. The image is beyond 2F, and this image is real, this image is inverted, and it's magnified. Image beyond 2F. This is for object between 2F and F. Now, what about for the object at 2F? The object at 2F, image is also at 2F. The image is real, is inverted, but the image has same size as the object, same size as the object. Remember, we have such a case in a curved mirror, a concave mirror, when the object is placed at C. Image is at C, the same size with the object, and it is real and inverted, just as it is here also. Now, what about the fourth one, where the object is now beyond 2F? If the object is placed beyond 2F, the image is formed between F and 2F. Object beyond 2F, now look at this very well. Object beyond 2F, image is between F and 2F. Look at this, object between 2F and F, image is beyond 2F. Now, object beyond 2F, image between F and 2F is the same thing we did when we said object between C and F, image beyond C. Object beyond C, image between C and F in the case of a concave mirror. You can see, go check those formation of mirrors, formation of images in a concave mirror. So all of these are important. Why? Because it shows us that, now remember, the kind of image we have here is real, is inverted, diminished. The image we have here is real, is inverted, same size with the object. The image we have here is real, inverted, and magnified. The image we have here is real, is inverted, and magnified. But the image we have here is virtual. So it means there is only one case where the convex mirror can produce a virtual image. What is that condition? The object must be between the principal focus and the optical center of the lens. That means every other cases will be a real image, and the real image is inverted, but the virtual image is erect. Now remember, the position, the distance between image and object is V minus U. The distance between the object's distance and the image distance. The distance between image and object is gotten by V minus U. But the distance between the image and the object in any of these other cases will be gotten by U plus V. That will be the distance between the image and the object. From the lens to the object is the object distance. From the lens to the image is the image distance. So the distance between the object and the image is called the image distance. Between the distance between the object and image is gotten by what now? U plus V. Now it's important to note that for a concave, take note of this, for a concave lens, take note, the image formed by a concave lens is virtual, is erect, and diminished. This is the only kind of image that a concave lens can produce, while all of these are the images a convex lens can produce. But a concave can only give us a virtual, an erect, and a diminished image. Now let's look at power of a lens. Power of the lens. The power of a lens is the ability of the lens to deviate the path of the rays passing through it. That's the power of the lens. How much ability has a lens to deviate the rays of light or the path of light passing through it. What's the formula for power of a lens? The power of a lens is the reciprocal of the focal length. That's 1 over focal length. If it's in meters, it's 1 over focal length. But if it's in centimeter, it's 100 over focal length. That's in centimeter. Now, what that's if the focal length is giving us in meters, is 1 over the focal length. But if it's giving us in centimeter, is 100 over focal length. What is the SI unit for the power of a lens? The SI unit for the power of a lens is diopter. That's the SI unit for the power of a lens. Diopter. Diopter. Let me spell that here. It's diopter. And is given as D as the symbol. Now we have a good example here on the power of a lens. The focal length of a concave lens is 40 centimeter. What is the power of the lens? To solve this question is just simple solution. We have power of a lens is equals 1 over focal length. But mind you, our focal length is giving us in centimeters, so it's equal to 100 centimeter over 40 centimeter over 40. So we have this cancels this, that's 100 over 40 centimeter. Now, what do we have now? We have power of a lens is equals 2.5 centimeter. Sorry, 2.5 diopter. The power of a lens is 2.5 diopter. Take note of this. The power of a lens is 2.5 diopter. But if you solve it this way, funnily enough, the answer is not correct. Why? Because the length that was given us is a concave lens, and the focal length of a concave lens is negative. So therefore, it means that the power of this lens is actually equals to minus 2.5 diopter. That's the power of the lens. Now, it can be from any other form. They will give you object distance, image distance, but you have to calculate the focal length because before you cannot calculate the power of the lens. Now let's look at questions, examples concerning calculations in length. Now please, if you look at this place, this is a convex lens, this is a concave lens. The focal length of a convex lens is positive, but for a concave lens is negative. This is a plano-convex lens. This plane surface is infinity. Why? This place is positive. The focal length of this plane surface is also infinity, while for this is negative. So that leaves us in the usage of 1 over f is equals 1 over u plus 1 over v. For a convex lens, the focal length is positive, but for a concave lens, the focal length is negative. It's very important. Then which other thing are we to note? We are to note also, remember we're using re is positive method, we are to note that For a virtual image, the image distance is negative. For a virtual image, the image distance is negative. And so it's very important you note this. Now, secondly, there are certain formulas that will be needed to ease calculation if magnification is added. Remember, we have magnification is equals V over F minus 1. We have magnification is equals 2V over arrow minus 1. We have again magnification is equal to F over U minus F. And we have magnification is equal to arrow over 2U minus arrow. These formulas will also be important as we look through questions in calculation of lenses. Why? Because a case where magnification is given us, we'll need these formulas to just hasten the calculation for easy calculation. Now let's look at example 1. It says for an object placed 6 centimeter from a diverging lens, from a diverging lens, from a diverging lens of focal length 18 centimeter. The image is that. So we have the object distance, which is 6 centimeter. We have the focal length, which is 18 centimeters. So I'll say 1 over F is equals 1 over U plus 1 over V. Now, the lens we are dealing with is a diverging lens. That's a concave lens. And for a concave lens, the focal length is negative. So it's 1 over minus 18 is equal to 1 over the object distance is 6 plus 1 over V. You take this where we have 1 over minus 18 minus 1 over 6 is equals 1 over V. LCM of 18 and 6 should be 18 times 6. So this takes off 18, remaining 6, 6 times 1 is minus 6, minus 6 takes off 6, is remaining 18, 18 times 1 is 18, is equals 1 over V. Minus 6 minus 18 will be minus 24. So I have minus 24 over 18 times 6 is equals 1 over V. So 6 here is 1, 6 here is 4. Then 2 here is 1, 2, sorry, 2 here is 2, 2 here is 9. So I have minus 2 over 9 is equals 1 over V. Therefore, what is V? V is minus 4.5 centimeter. So my V is minus 4.5 centimeter. Now, if you look at the way the options were giving us, it does not show us a minus sign. Why? Because the minus sign is indicating something. What's the minus sign indicating? It indicates that the image is virtual. That's what the minus sign is indicating to us. The image is virtual. Now the question is now where is the position of a virtual image in a diverging length? Where is the position? Is it behind or in front? Is it behind or in front? Now, there's something you must know about a diverging or a virtual image. It's always behind the lens. The image is virtual, means it is behind the lens. So the answer to this question is B, 4.5 centimeter behind the lens. Thank you. Now let's see example number 2. It says a concave lens of focal length 15 centimeter forms an image 1 over 3 the size of the object. The image is diminished. A diverging lens will give us a virtual and a red and a diminished image. Now, when I said the object distance is dash. Now, if you look at this number 2, we have focal length is equals, focal length is 15 centimeter, and we have magnification is equals 1 over 3. We are asked to look for our object distance. So what formula has magnification, has focal length, and has object distance? We'll be using M is equals F over U minus F. This formula will help us to get it at once. Now, what about magnification? 1 over 3 is our magnification. is equal to, what about our focal length? Our focal length is 15 over u minus 15. Now, this is very important. Why? Because we are dealing with a concave lens. If we are dealing with a concave lens, the focal length of a concave lens is negative, and the image, now let me do that first. The focal length of a concave lens is negative, meaning I will add minus 15 to 15 and also come here and make here also minus 15. So it's now u minus 15, because the focal length of a concave mirror, of a concave lens, is minus 15. That's very important. That's very important to note that. Now, what is another thing we have to note in this question? The image formed by a concave lens is virtual, is erect, and is diminished. Now, if it's virtual, it means that the magnification is negative. If it's virtual, the magnification is negative. So I have introduced a negative sign here. I've introduced a negative sign here, and I've introduced a negative sign here. You remember when we solved the first question, we had minus 4.5. We said is because the image is virtual. Now I'll progress in my calculation. This calculation might look difficult. Why? Because of the fraction in cross multiplying. So instead, I will take this to become decimal. So in 1 over 3 becomes minus 0.333 is equals minus 15 over, this becomes u plus 15. Minus times minus is plus. So now I cannot cross multiply. If I cross multiply, I will have, this will not be, if I cross multiply this, I will have minus 15 is equal to minus 0.333 open bracket u plus 15. That's very important. So now what do we have now? We have minus 15 is equal to minus 0.333u plus times minus is minus, minus, you have 4.995. Now, what's the next thing we do here? Let's collect like terms. Let this go here, let this go this way, and let this come this way. So we'll be having here as 0.333u is equal to minus 4.995 plus 15. Now, what's that the next thing? If you do this, we now have 0.333u is equals, this would now become 10.005. So what is u equal to? Our u will now be equal to 30 centimeter. That's the answer to this question. Please follow the way I solved and see the clarity for understanding. So the u is now 30 centimeter. That's for this solution. Now let's look at question number 3. Question number 3 says, an object placed 12 centimeter in front of a convex lens produced a virtual image. Produced a virtual image from a convex lens. A virtual image from a convex lens. You know that a convex lens can produce both virtual and real images. So it will produce a virtual image when the object is between the principal focus and the optical center of the lens. Now, what's about it? It said a virtual image of magnification 3. The focal length of the lens is dash. Now we have object distance. Our u is equal to 12 centimeter. We have magnification is equal to 3. And we are looking for f. We are looking for f. F is unknown to us. So which formula will help us solve this? We'll use magnification is equal to f over u minus f. F over u minus f. So this is 3 is equal to, what is our f? We don't know that yet. Over, what's our u? 12 minus f. Now, mind you, the image form is virtual. So because the image form is a virtual image, therefore I will add a negative sign to my 3 because the image was virtual. Now, continuation, I have f is not equal to, cross multiply this. We have minus 3 open bracket 12 minus f So that becomes f is now equals minus 3 times 12 is minus 36. Minus times minus is plus. 3 times this is 3f. Now collect your like terms and make it simple for you. Let 36 come over. It becomes 36 is equal to, let f go behind, is 3f minus f. So I have 36 is now equals 2f. Therefore, f is now equal to 36 over 2, which is now what now? 18. 18 centimeter rather. So the focal length is 18 centimeter. Now take note, the focal length is positive. Why? Because the focal length of a convex lens is positive, but the focal length of a concave lens is negative. Thank you. Now, please endeavor to take a past question and go through other questions and see things easy for yourself. Thank you.